In this video, I'm going to be going over a couple examples in which I'm going to verify that a certain explicit solution, or verify that a certain function is an explicit solution of some given ordinary differential equation. Alright, so let's just get into it. So my instructions for both examples in this video are to verify that the indicated function is an explicit solution of the differential equation. Here we're assuming an appropriate interval I of definition for each solution. Remember, the interval of definition for a solution is any interval on which the solution is defined and also differentiable. All right, it's an interval for which the solution is defined and is also differentiable. Now, you'd like to make the interval of definition as large as possible when writing it out, but for here we're not going to be writing out the interval of definition. Right? Although you should think about that, whenever you come up with a solution for a differential equation, you should be thinking about on what intervals, what's the interval of definition for this solution. Anyway, all right. So here's the differential equation. It's a first order linear. You have 2 times y prime plus y equals 0. And the function in question is this over here, right, where y is expressed as a function of a variable x. So y equals e to the negative 1/2 x, right, negative x over 2. Alright, so let's go through and do its test, verify that this actually satisfies this differential equation. Alright, so I can substitute e to the negative x over 2 for y. I need to figure out what y prime is and substitute for y prime and see that this equation holds. Alright, so hopefully you remember your calculus, right? Differentiation. If y is e to the negative 1/2 x, y prime would be, it's an exponential, so it's itself e to the negative 1/2 x. But then chain rule times the derivative of negative 1/2 x with respect to x would be negative 1/2. Right. And there, now I have y prime. I substitute them into the equation. And verify that this is a true statement. Okay. So we have 2 times y prime, which is this negative 1/2 e to the negative x over 2. Plus, and then y. Now, since y is not being multiplied by anything or raised to any powers, I'm not going to put parentheses around it. Y is just e to the negative x over 2, negative 1/2 x. And, is this equal to 0? Well, yes, right, because 2 times negative 1/2 would be negative 1, so negative e to the negative x over 2 for this first term, plus e to the negative x over 2 for the second term equals 0, and then yes, you have 0 equals 0, check. All right. So this function, y equals e to the negative 1/2 x, this is a solution to this differential equation, a particular solution, and it's it's an explicit solution, right? Because you have y written strictly as a function of x, y equals, and then function, the dependent variable on one side equals, and then some expression involving the independent variable on the other. Okay, and that's all it takes. Now I think I said I wouldn't do this, but the interval of definition here for this solution. This is an exponential. This is defined everywhere and differentiable everywhere. All right, there's there's no point in which this isn't defined. Same thing for the derivative. There's no value of x for which this is not defined. So the interval of definition here would be all real numbers from negative infinity to infinity. But again, you didn't have to do that. Right. Okay. So just got one more example. Again, I can't possibly go over every possible example of what you're going to come across. I just wanted to throw out a couple. How would you verify? It's very simple. You just take as many derivatives as you need. Just look at the order of the equation. That's how many derivatives you're going to need to go to, and then substitute and check to see that it actually works out. All right. So I have one more example. All right, here's a second order equation. So y double prime minus 6 times y prime plus 13y equals 0. Again, I'm going to try to verify that this, here's the function in question, an explicit function, fun. Y equals e to the 3x times the cosine of 2x. Now again, it's a second order equation. So in order to verify that this is a particular solution to this equation, that it satisfies it, I need to get to the second derivative. All right, so we have I'll do this here, y prime. Now it's a product. All right, so I'm going to be using the product rule, and there's some chain rule involved as well. Right. So remember how that goes. The product rule, the first factor, e to the 3x, times the derivative of the second factor. Hopefully you recall, the derivative of cosine was negative sine. So that'd be negative sine of 2x and then times 2. So I'll have negative 2 out front here. Negative 2 times e to the 3x times sine of 2x. Then plus, and then leave the second factor alone, cosine of 2x. And the derivative of e to the 3x would be e to the 3x times 3. Okay. Great. Here's the first derivative. And then I do the same for the second. Right, now you could factor out an e to the 3x from this. And if you'd like, I'm just going to leave it the way it is and apply the product rule to both these terms. Alright, so here I'd have, I'm doing the derivative of this first term, I'm using the product rule again. So I have negative 2 times e to the 3x, and then times, cosine of 2x times 2, so it'd be negative 4 e to the 3x times the cosine of 2x. Then plus, leave the sine of 2x alone, and then the derivative of this first factor would be e to the 3x, times 3 again would be minus 6 e to the 3x times sine of 2x. Okay, and then I'm going to do the same thing for the second term. All right, so 3 e to the 3x times the sine of 2x, but negative sine of 2x times 2, so that'd be minus 6 minus 6 e to the 3x sine of 2x, and then keep the cosine 2x, and then the derivative of e to the 3x would be 3 e to the 3x plus 9, right, plus 9 e to the 3x cosine 2x. Alright, so there's the second derivative, and I'll combine some like terms here. See, e to the 3x cosine 2x, those terms are in common, so I have 5 of those, negative 4 plus 9. And then same thing with the e to the 3x times the sine of 2x terms. I got minus 12 of those. Okay, so there's the second derivative. Now I'm just going to do some substitution. Substitute this for y double prime, this for y prime, and this for y, and see that I get a true statement, 0 equals 0 here. Alright, so the y double prime isn't multiplied by anything, so I'm not going to do parentheses. So here's substitution. I'm just going to put sub there. So we have y double prime, which is this 5e to the 3x times the cosine of 2x, minus 12e to the 3x times the sine of 2x, and then minus 6 times y prime. Right? So I'm putting parentheses here. This is all y prime, which was this expression here. We had negative 2 e to the 3x sine of 2x plus 3 e to the 3x cosine of 2x. Sorry about the edge of the page there. And then finally plus 13y. Well, 13 times y is this e to the 3x cosine of 2x. And then you have equals 0. Now, hopefully, right, if this truly is a solution and I did my derivatives correctly, this should end up being the true statement, like 0 equals 0. Right. Well, let's see. Let's kind of eyeball it here. I distribute the negative 6 to these two terms. And that'll give me positive 12 e to the 3x sine of 2x. Well, over here there's negative 12 e to the 3x sine of 2x. So this will go away when the negative 6 is distributed here. Then negative 6 times 3, and that's negative 18 e to the 3x cosine 2x. And negative 18 plus the 5 plus the 13 of that e to the 3x cosine 2x makes 0. So everything's gone. Wonderful. And I have 0 equals 0, a true statement. Check. That is this particular function. Right, this function is a particular solution to this differential equation. And again, this isn't always going to happen, but the interval of definition for the solution, where it's defined and differentiable, and without any breaks in it or any gaps. The largest of these, again, is an exponential times a cosine or times a sine. All the derivatives, these are all this function, its first derivative, its second derivative are defined everywhere. So again, the interval of definition for this solution would be all real numbers, but that's not, again, please know that this is not always going to happen. All right, we'll see examples in other videos, I'm sure, where the interval of definition is not all real numbers. Now, of course, I could make it smaller if I wanted, or I could really have any interval here, but we usually will just take the largest interval, where the solution is defined and differentiable, and there's without any breaks in the interval. Okay. All right. So again, just a couple examples here where I went through and verified that a given explicit function was a solution to a given differential equation. Hopefully these examples made sense and help you out when you're working on problems similar to this on your own. And thank you very much for watching.